Good morning, ladies and gentlemen. Let's go ahead and make a connection between a function's derivatives and its graphical behavior. And so, complete each statement. Go ahead and share with the class when I call on you. When f is increasing, then f prime is blank. Hayden? Positive. Positive. Raise your hand if you have the same as Hayden. Positive. Positive. Great. If f prime represents the slope or rate of change of the original function f anywhere along it, then a positive rate of change would represent increasing function behavior in f. When y is decreasing, y prime is blank. Negative. Negative. Raise your hand if you have negative for the second one. Negative. Way to go. Very nice. When y has a horizontal tangent, then dy dx equals blank. So when y has a horizontal tangent, what must be true about dy dx? Tyler? Zero. Zero. Raise your hand if you had zero for that third one. Zero for the third statement. Great, thanks. Where dy dx is undefined, y could have a blank, or a blank, or a blank. Oh, goodness. So when dy dx is undefined, then what could be going on at the same x equals c value on the graph of y? So what's one thing that could be going on? Right? What's one thing that could be going on? James?
A vertical asymptote.
A vertical asymptote. Good. A vertical asymptote would represent an infinite discontinuity. And we know that our original function y, if it has a discontinuity, any kind of discontinuity, then dy dx is undefined. So I'm going to go ahead and say discontinuity for that one, because that takes care of vertical asymptote. Right? What type of discontinuity is a vertical asymptote? An infinite discontinuity. Good. Besides from discontinuity, what else could be going on, right, on the graph of y if dy dx is undefined? So what's another feature that y could have at that place? Kobe and Courtney?
A cusp.
A cusp, right? We could be not a discontinuity. We could be continuous, but an abrupt change in direction, right? If the left-hand slope doesn't match the right-hand slope, that graphically is a cusp, and dy dx is undefined at that abrupt change in direction. So a cusp, right? A cusp is another feature y could have when y prime is undefined. Excellent, thank you. All right, go ahead and tell your partner if you can get the third thing. All right, what was the third thing? I lumped all the discontinuities together, even though there's three of those. I took that all in one, so we're down to the wire. Oh, one more thing. Hang on, don't call out, guys. You're going to spoil everybody's puzzle. Don't spoil my puzzle. All right, so what's that last thing, Sammy and Michael? Vertical tangent. So we could be continuous, right? We could even be smooth. Right? No abrupt change in direction, and yet we could be undefined dy dx if there's a vertical tangent, such as the case with like the cube root function. The cube root function is continuous for all values of x in this domain. Right? There's no corners, kinks, or cusps in y equals cube root of x, and yet dy dx is undefined at x equals 0 because there's a vertical tangent, and we know a vertical tangent would have a slope that's undefined. If y prime represents the slope, then that would be an undefined y prime. Absolutely. So vertical tangent is our third feature that could be going on with y. I'll call that. Awesome work, you guys. What questions do you have about your Bellwork questions? And that's getting us set up and thinking about our graphical behavior today. We're going to use derivatives to analyze the graphs of functions and describe function behavior using calculus. Okay, but first, I can't wait for some of you to realize how well you did on your Unit 7 test. For example, the indefinite integral of 1 over y squared with respect to y. I saw several different answers for these, one of which is correct, right? And so I just want you to be thinking about, and we saw this earlier, is this a natural log? No. Why isn't this a natural log, James?
Y squared is on the bottom, has to be like y to the first.
Absolutely. And so while natural log is a candidate for use in an antiderivative rule when we have a quantity on the bottom to the first power, right? This particular example, integrand function has y to the second power on bottom. Overall, this is just a power rule, right? This is just a power rule. So don't use natural log to integrate a fraction. Remember we talked about one of the top 10 student errors was using sort of logarithmic anti-differentiation universally. Anytime there's a fraction, we think, oh, that's an ln rule. No, only if we have a quantity on the bottom to the first power, right? And if that derivative of the quantity exists or is present, then we can use a natural log. Okay, let's go ahead and take care of our big, massive homework check. We've got two separate checks today. So what we're going to do is we're going to do this separately. The first thing is going to be your Unit 7 review. And we had a whole slew of things. And so I'd ask if you kindly staple these together. We've got slope field and sample practice and matching out of 13. We've got your short matching out of 6. Pick the tricky ones. The 2006 free response number 5. I did one for each letter for a total of 3. And then your book review problems, the R's and T's for a total of 17. That adds up to 39. So what I'd ask that you do while you're waiting for the stapler to make its way around the room is go ahead and give yourself credit in pencil for those you completed out of 39 on your review assignment. This does not include the science diagram worksheet. We're going to turn that in separately. So please do not turn in the science diagram worksheet. We're going to do a separate collection for that. If you've already stapled them in a different order, that's totally fine. Wherever you stapled on top, you need to put your infinite gamma score nice and big in box. Also make sure that you got your name, first and last, 1A, and then review label. Don't include science diagram worksheet in this one. No, just your OTL number 0, prerequisite skill review.
Sorry.
It's okay, just 2 checks. That'll be the next check. This one is just the review. So everybody, just the review right now. Okay, ladies and gentlemen, so in just a minute, we're going to go ahead and take our findings from our Form A through D, right? You're going to report back to your group, and we're going to go ahead and make some generalizations about the connection between an original function y and then its first and second derivatives, y prime and y double prime respectively. But first, let's go ahead and get some common vocabulary that we'll be using. So everybody on your day 1 note sheet, let's everybody find extrema. Extrema, right, comes from extremes. We're talking about maximums and minimums of functions. We've got a couple different kinds. So the first kind we'll refer to as relative maxes or relative minimums, also called local maximums or local minimums. Graphically, these are the greatest function value attained in a given locale, right? In some small window, this is the largest or the smallest function value that's attained over some arbitrarily small window. Informally, you recognize local maximums, right, as the tops of a peak, or relative minimums as the bottom of a valley. Keep in mind that we could have a cusp at a relative extremum, or it could be nice, smooth, and well-behaved. However, in each case, we're talking about the greatest function value attained on some arbitrarily small window, or the smallest function value attained. Versus absolute maximum or absolute minimum, also referred to in some texts as a global maximum or a global minimum. This is the greatest or least function value on a specified interval. So in the first case, when we talked about some arbitrarily small window, right, some viewing window, we're talking about like the top of a peak or the bottom of a valley. An absolute maximum could also be the top of the peak or a bottom of a valley, if they're greater or lesser than the endpoints of that specified interval. And so the only difference with absolute maxes versus mins is you have to take into account the endpoint values of that interval and compare them with any local maximums or minimums that are included within it. And so now we're talking about still the possibility of having a peak, right, or a valley. It's just that now we have to consider, right, endpoints of the intervals. I kind of want to like this. Okay, so this is a great picture because right? In one case, we've got a local minimum that's also a global minimum because it's not only the least most function value attained on some arbitrarily small window, making the bottom of a valley or the top of a peak, in this case, the bottom of a valley, but it's also the least value function attained over the specified interval from green point to green point. So this is both a local max and a local min in this case. So that would be a local max and a local, I'm sorry, global. Talking and writing is hard. A local minimum and a global minimum, an absolute minimum, because it's the least function value attained over the entire interval. Oh, Emmy's gone today, so I can give that back to him. And thank you. So we've got a local minimum and an absolute minimum, which is what I might say the whole time. All right, so should we label these local minimum, local maximum, and local minimum, global minimum, and what's going on here? Well, here we've got a local maximum. Is that local maximum also the global maximum? No, because it's not as high as this, right, function value, and this happens to occur at the end point, and so this is a candidate for absolute as well. So here we've got absolute maximum versus local maximum. Slow down, right, speak. Awesome. So intuitively, that stuff makes sense. The only tricky part can be sort of the consideration of the endpoints. And so local maximums and local minimums, right? We're talking about some arbitrary window versus absolute maximums and absolute minimums. We're talking about some specified interval, and we must include the endpoints of our interval in the discussion before we can include or determine the absolute versus the local experiment. All right, critical values. So named, right, because these are the only places where my function can change direction. So critical values, or this text calls them critical points. Y has a critical value, or critical point, where 1, y prime equals 0, or 2, y prime is undefined. Those are our only possibilities for y having a critical value. Those are the only places where y prime might change direction, right? So that is switch from increasing to decreasing, or vice versa, switch from decreasing to increasing. So the only places where y can change direction are at critical values. So part of our analysis, right, is going to be determining where y prime equals 0 or y prime is undefined, and we're going to use that now to analyze the function behavior of y. Concavity, you guys also have a good understanding of, right? Concavity is the shape of a graph, the shape of a graph. And so we can think about concavity in terms of being concave up. That's representing part of a right side up bowl shape. Versus concave down. That would be part of an upside down bowl shape. Notice how, while a function is concave up, it could either be increasing or decreasing, like a parabola, right? In each case, though, over this entire interval, the function is concave up, because no matter where you look in this green graph, right, it would be part of the sides of a right side up bowl shape. Concave down, no matter where you look, whether it's increasing portion of the graph or decreasing portion of the graph, still adheres to kind of an upside down bowl shape. Great function would be like y equals x cubed. Y equals x cubed is smooth and differentiable for all values of x. In fact, y prime, right, if y equals x cubed, y prime is going to indicate positive, right, increasing behavior rather on y equals x cubed. Everywhere except at x equals 0, where y prime equals 0. For all other x values, the function is increasing, and yet we change concavity here. So when we switch concavity, this left half of the graph is really concave. Would you say this is concave up or concave down on the left side? Concave down, so this would be concave down behavior. On the right side here of the graph, y equals x cubed exhibits concave up behavior. And at this little hash mark that I've done here, when a function switches concavity, you know that's called an inflection point, or a point of inflection. And so y has an inflection point. Y has an inflection point if and only if y switches concavity at x equals c. Awesome. Okay, so in just a minute we're going to scooch into our groups and we're going to focus on how the behavior of y prime and y double prime affects, right, the original graph of y. And we're going to do this by sharing your results from your form A, B, C, and D. Before we do that, however, we're going to go ahead and take a look at our questions that we're going to be able to answer at the end. I'd like for you guys to generalize your findings in pencil, right? Write down lightly in pencil because we're going to be sharing with the class after the jigsaw. And then when we come together and formalize the notes together as a class, then I want you to go ahead and fill in either with pen or your final version, because there are, right, some important things I want everybody to have, even regardless of which group they were in, okay? So once again, lightly in pencil for your conversations, be jotting things down, be willing to share those things and pieces of information, and then when we come back together for our formal discussion, then I want you to darken up, either use pen or get some common things that we want everybody to have. At the end of our jigsaw, we need to be able to address, 1, how does the sign of y prime affect the behavior of y? I think we already are close to that one. 2, a horizontal tangent on y corresponds to what feature on y prime? 3, how does the sign of y double prime affect the behavior of y? 4, when y changes curvature, what happens to y double prime? 5, if y has a local extremum, that is a maximum or a minimum, at x equals c, what must be true about y prime at x equals c? And 6, if y has an inflection point at x equals c, then what must be true about y double prime at x equals c? These are the questions that we're going to address when we return. On a given interval, a global extremum may only occur at a blank or a blank. Awesome. All right, so I'm going to go ahead and pause the recording, and then we're going to scooch into our groups and pay close attention to those questions. So let's go ahead and see now how the behavior of y prime and y double prime, right, dictate the graph of my original y. So how does the sign of y prime affect the behavior of y? And we have some common things that we've seen regardless of which form you had, A, B, C, or D. So how does y prime affect the behavior of y? How does the sign specifically positive versus negative? Joel?
When y prime is positive, y is increasing. When y prime is negative, y is increasing.
Awesome. And so when y prime is positive versus y prime negative, it has different effects on my behavior of y. Joel says when y prime is greater than 0, that is positive. And what's y doing? Y is increasing. When y prime is less than 0, when y prime is negative, that means that y is decreasing. Thank you. A horizontal tangent on y corresponds to what feature, right? What graphical feature on y prime? So this should have been true regardless of which group you're in or which form. If y has a horizontal tangent, then what must y prime have at that same x equals c value? What feature must y prime have? Riley, Fi?
Yes. it must be a 0 of y prime.
So y prime must have a 0 or an x-intercept if y has a horizontal tangent. Absolutely. So y prime must have a 0 / x-intercept. So y prime has a x-intercept or a function 0 when y has a horizontal tangent. Awesome. All right, so who got 1 and 2? All right, who already got 1 and 2 already from your group to discussion? Great. Now, let's take a look at y double prime. How does the sign of y double prime affect the behavior of y? So what did you guys find for that? Annika?
It changes like the curvature.
Yep. And how so? What about the signs of y double prime?
And it's positive. It's an optical, I think.
Yeah, a right side up bowl shape, and what do we call that? What do we call that left side of the graph? Of the cubic function?
Concave up.
Absolutely. And so y double prime, if it's positive sign, then y is concave up. And then the other case, Annika?
Then it's negative. When it's out.
If what is negative, then what is concave down?
Oh, y double prime is negative, then y is concave down.
Absolutely, and that's been a big point from the graders as a result of the AP exam grading tables is using the pronouns like it, right? Automatically assuming the grader is going to connect the antecedent with the proper right noun, and so we want to make sure that we're saying specifically y does what when y prime does what when y double prime does what. We can't just say it's increasing when it's positive. Well, it's not increasing when it's positive depending upon what it you choose. Y is increasing, right, when y prime is positive, but y prime isn't increasing when y is positive necessarily, and so we have to be careful with our ifs and everything. Absolutely, perfect. Thank you, good. Awesome. When y changes curvature, what happens to y double prime? We had a couple questions that addressed the same thing. My hope was that as a result of looking at the different functions, there are several different functions, when they change curvature, we could go ahead and narrow it down to a specific thing for y double prime. So y changes curvature, what happens to y double prime? Y double prime must change sign in order for y to switch concavity. So the bold thing that I want everybody to get down for number 4, y double prime must switch sign. So y double prime must switch signs from either positive to negative or negative to positive in order, bless you, for y to change curvature. Okay? It's not enough for y double prime to have an asymptote or y double prime to have a 0 or an x-intercept. In order for y to change curvature, y double prime must switch sign from either positive to negative or vice versa, negative to positive. Good. Let's take a look at 5. If y has a local extremum, that's either a maximum or a minimum, at x equals c, what must be true about y prime at x equals c? And so if y has a local extremum, that is a max or min, at x equals c, what must be true about y prime at x equals c? So who found some generalizations for this one that they're willing to share? A couple different things. Brandon?
Oh, I only have one thing,
Okay.
and that's y prime equals 0.
So if y prime equals 0, right, then y may have a local maximum or a local minimum. Good. If y prime equals 0, what feature would y have graphically? Y prime equals 0.
Asymptote.
It would have a what?
A horizontal asymptote.
A horizontal tangent, right? A horizontal tangent, absolutely. A horizontal tangent, right? A horizontal tangent could be a place where y changes from increasing to decreasing, or from decreasing to increasing, signaling the presence of a local max. However, consider the graph of y equals x cubed. Y equals x cubed has a horizontal tangent at x equals 0. In fact, the first derivative of y equals x cubed, y prime equals 3x squared, equals 0 at x equals 0. There is a horizontal tangent at x equals 0. And yet, does y equals x cubed have a local extremum at x equals 0? No. Is this the greatest function value attained in a given locale? No. As soon as you start looking in the arbitrary window, I can find larger values to the right of x equals 0, right? And smaller values to the left of. And so at x equals 0, that's neither a local maximum nor a local minimum. And so it's not enough for y prime to equal 0 for y to have a local maximum or minimum, right? What does y prime have to do? Sandy?
Oh, I was just gonna say, our if then goes the other way though. So I mean, if y has a local extremum, then y does have to equal 0. I mean, y prime does have to equal 0.
As we consider the graph, this one, raise your hand if you have this graph. Go ahead, this graph. Yeah, okay, so I see a local maximum right here in my original y. That's a local maximum. How come? Because it's the top of the peak. It's the greatest function value attained in a given locale, an arbitrary window on either side. This is the greatest function value attained in this arbitrary window, this given locale. That's why it's called a local max. Yes? So who had the y prime picture for this? Did y prime equal 0 at x equals 0? No, what did y prime do? Well, at x equals 0, y prime must be what, given this picture? Undefined, for sure, right? Now consider the signs. Before x equals 0, right, my values of y prime were getting larger and larger as this gets steeper, yes? After x equals 0, my values of y prime were negative, yes? Indicating this decreasing behavior. So even though there was a discontinuity on y prime, it had to go from positive values to negative values, right? And so I don't want you to think that we have to have y prime equals 0 in order to have a max. What we need to do is similar to our inflection point. Y prime must change sign at x equals c in order for f to have a local extremum. So again, we must change sign. If y prime equals 0, then that's a candidate for having a local maximum min at x equals c. But in order to have a local maximum or a local min, then y prime must change sign. So y prime must change sign at x equals c in order for y to have a local extremum next. All right, if y has an inflection point at x equals c, what must be true about y double prime at x equals c? And this is the same question as our number 4, right? If y changes curvature at x equals c, y has an inflection point at x equals c, y double prime must do what? Has to change sign. So this is an important activity because we're going to be, in the coming days, getting candidates for these special points. A candidate for a local extremum. A candidate for a point of inflection. We still have to go and do a sign diagram analysis in order to determine if that corresponding derivative changes sign in order to guarantee that feature. So this is a great discussion. So when we say, you guessed it, y double prime must change sign. So y double prime must change sign at x equals c in order for y to have an inflection point. Awesome. I do want to give you, we're going to do an 18 practice. How hot? Too hot. Okay. And we're going to go on a given interval, a global extremum that is absolute max or min may only occur at And we've got two options here. One, it can occur at a critical value. So we saw critical values where when y prime equals 0, y prime was undefined, or at an endpoint. So on a given interval, a global extremum may only occur at a critical value or at an endpoint. Now keep in mind this is a little bit loaded because a critical value is two different places, right? There's two different kinds of critical values. A critical value exists when y prime is undefined or when y prime equals 0. So y prime equals 0, y prime is undefined. But just because we have a local max, right, or a local min doesn't mean it's a global maximum or a global minimum. We must compare that function value obtained with the function values of the endpoints of the interval. Then I can ascertain what is the absolute maximum on a specified interval. What is the absolute minimum on a specified interval? Okay, lots of stuff, and then we're going to do a little practice. And so let's go ahead and summarize our findings in 3 different charts. Firstly, Joel told us that when y is increasing, y prime is positive. When y is decreasing, then y prime was negative. And we know when y has a horizontal tangent, then y prime must equal 0. The new thing that we added today involves critical values of y. Y has a critical value if and only if y prime equals 0 or is undefined. So we've got 2 different possibilities there. Why is it called a critical value? Because that's the only place where y could change direction. It doesn't mean that it does change direction. It's called a critical value because that's the only place where y could change direction, could change behavior. And we care about that for finding things like maximums or minimums, right? Optimizing situations, which is a big application of differential calculus we're going to look at this unit. Consider the relationship now between y and y double prime. We know y is concave up when y double prime is positive. And Annika told us that y was concave down when y double prime was negative. If we're determining the points of inflection on y, then we've got possibilities for points of inflection whenever y double prime is 0 or undefined. Bless you. Keep in mind that doesn't mean that y has a point of inflection when y double prime equals 0 or is undefined. It means that we've got a candidate for a point of inflection. We must see if y double prime changes sign. Okay. And lastly, a connection between y prime and y double prime. And so if we're on our calculus ladder, all right, and we've made an explicit connection between the signs of y prime and y, we can then step down one rung in those relationships between y prime and y double prime, that's just one derivative apart, right, must still exist. Therefore, if y prime is increasing, what must be true about y double prime? If y prime is increasing, what must be true about y double prime? Colin?
It must be positive.
Absolutely. And so positive y double prime must indicate increasing behavior on y prime. Negative y double prime values must indicate decreasing behavior in y prime. And you guessed it, if y prime has a horizontal tangent, then y double prime must equal 0. Awesome. So we're going to have a chance to practice, and I gave Megan one on her way out. With OTL number 1, you've got a nice chunk of time here to work. I'm going to include function behavior sketching 8.2 for a stamp. I was going to hold off to next time, but we've got a nice chunk of work time, and so this would be a good thing to do as a partner. 8.2 sketching functions, or graph sketching. is going to be for a stamp. And you must check, right? Must check with the 8.2 key. It's in the chart for Unit 8, Day 1, okay? So we've got a stamp at the end of 8.2, and I'm going to distribute that now, and you may work on that together. I'll go ahead and stop the recording and upload it to our Moodle.